Hi everyone, welcome to Best Science Brain YouTube channel. Today we are taking a look at WAEC Physics 2024 Practical Physics Alternative B, May, June 2024, number 3 question. So in this experiment, we are provided with a meter rule. You can see AB is uniform meter rule. And the meter rule is suspended at point O, which is the 10 cm mark, and also point Q, point O, the 10 cm mark, and point Q, the 90 cm mark. So, by two vertical strings, the strings are SY and then PQ. And the strings are maintained at a height or length of 70 cm. H is 70 cm, so equal height on both sides. And this height, 70 cm, is kept constant throughout the experiment. So you see that the meter rule is clamped on two rotor stands, one by the left-hand side and one on the right-hand side, and are held in support by two strings. The two strings that are inclined at 90 degrees to the clamp are SY and PQ. The height of the strings are 70 cm each. They are vertical strings. The meter rule is AB. The center of gravity of the meter rule is the point C. The point C, the center of gravity of the meter rule, which you're going to determine using a knife edge. And a mass is going to be placed at the center of gravity. The mass is M, and the meter rule is set into 20 vertical oscillations. 20 vertical oscillations. And then we use the stopwatch to time the time taken for the meter rule to perform 20 vertical oscillations. The distance from Y, where the meter rule is supported on the left-hand side, to Q, the 90 cm. The point Y is the 10 cm, where the meter rule is being held by the string SY, and 90 cm, where the meter rule is being at Q, where the meter rule is being held at by the string at Q. The distance between the Q and Y, that is 10 to 90 cm, is represented using the letter D, and that distance is 80 cm. So in this experiment, two things are held constant. The length of the string H, that is SY or PQ, is 70 cm. So it will be held constant all through the experiment. And the distance from Y to Q, where you have the strings holding the meter rule, that distance will be held constant as 80 cm. That means the meter rule is clamped or is supported by the string at 10 cm and also at 90 cm, from both 10 cm from the 0 end and 90 cm from the 100 end. So that means the distance YQ will be 90 minus 10. The D is 80 cm. So these two things will be held constant throughout the experiment. While the mass at the center of gravity, the mass will vary, will be changed from point to point, and the meter rule is made to oscillate or undergo 20 vertical oscillations. So let's understand this experiment. It's more like simple pendulum, but it's not simple pendulum. It is different because in simple pendulum, the length of the pendulum is changed constantly. But in this experiment, the length of the string held in the meter rule AB will be held constant all through the experiment, will be maintained, whether it's 70 cm, whether it's 80 cm, or we know that the height PQ or SY will be held constant all through the experiment, and the distance between the two strings, which is D, will be held constant also all through the experiment. So what we're going to change is only the mass that will rest on the center of gravity, 30 gram, 40 gram, 50 gram, and so on. So once each mass is placed at that center, the meter rule is then subjected to 20 vertical oscillations, In this our work, we're going to use 20 oscillations, where you can see tell you to do it 10 oscillations or 30 oscillations. Whatever case it is, it remains the same procedure. So let's look at the question. Question goes thus. A. You are provided with a set of masses, meter rule, a thread, 2 retort stands and clamps, a stopwatch, a knife edge, and split corks. Carry the following instruction using the diagram above as a guide. I. Determine the center of gravity, C, of the meter rule using the knife edge. The center of gravity is this point where the meter rule balances when there's no mass on it. So before we hang the meter rule, as have it on the diagram, we have to find the center of gravity, balance it with a knife edge. And for uniform meter rule, the center of gravity is always at the midpoint. A meter rule is 100 cm in length. Center of gravity, in the absence of air or any other resisting factor, will be at 50 cm. So that C will be taken as 50 cm in this our calculation. 2. Read and record the mass M of the meter rule written on the reverse side of it. So, in this experiment, you may not be asked to read and record the mass because WAEC did not tell us to measure the mass of the meter rule, but the mass is required for this experiment. So, what do? So, we have to take a standard mass. So, wooden meter rules in the laboratory have masses ranging from 100 grams to 200 grams, uniform meter rules. So, in this experiment, we take a mean mass, which is a standard mass. We're going to use the mass of the meter rule as 150 grams. 150 grams. So you can use our own mass, and then, or you can use any mass, 120, 130, 140, 150, 160. So we're using 150 grams or 0.15 kg in this experiment. So if you follow our calculations the way it should be, then you have to work with 150 grams or 0.15 kg. Unless you change your mass, then you change your calculations also. So 3. Suspend the meter rule by means of 2 parallel trays of equal length, h equal to 70 cm, with one at 10 cm mark and the other at the 90 cm mark of the meter rule. So that what we are trying to explain. You can see the first string SY, the height h, that height is 70 cm, h is 70 cm, and then the point y is 10 cm, and the other meter rule, the other string, PQ, suspended at Q, that Q is 90 cm, the height is also the same 70 centimeter. When I go to question number IV, attach a mass M equal to 30 grams firmly on the meter rule as C, the C center of gravity. Ensure that the graduated face of the meter rule is facing upwards, and that D is 80 cm throughout the experiment. So let's look at what they are talking about. So after we have done all this, you bring them a mass of 30 grams and place it at the center of gravity. That is the 50 cm mark, is the uniform meter rule. So, and then we ensure, as we say, that D is constant, that the distance between Y and Q remains 80 cm, no change. Then the height, the 70 cm height of the string remains constant all through the experiment. V. Set the meter rule into small angular oscillations about the vertical axis through its center of gravity by displacing its ends in opposite direction. So you're going to hold the ends of the meter rule slightly, the 0 end and the 100 cm end, and then displace it to set it into vertical oscillations. Then VI, determine the time T for 20 oscillations. So make it oscillate for 20 times. You have to switch on your stopwatch as the oscillation begins and evaluate T, capital T. The small t is the time for 20 oscillation. The capital T is the period. Capital T period is nothing but the time for oscillation all over the number of oscillation. Then period squared and the inverse of period squared. VII. Repeat the procedure for 4 other values of M. So the first M was 30 gram. Then repeat with M equal to 40 gram, 50 gram, 60 gram, and 70 gram. In each case, determine the time, that is small t, for 20 oscillations and evaluate capital T, that is the period squared, and t raised to power minus 2. VII. Plot a graph of the inverse of t squared on the vertical axis against M on the horizontal axis. Then I determine the slope S of the graph. Then V, evaluate Q equal to 0.68 over S. Then SI, state 2 precautions taken to ensure accurate results. Then BI, give 2 examples of simple harmonic motion other than the motion of a simple pendulum. And then I explain the term center of gravity of a body. So before we go on to this experiment, in this video we are doing calculations, how to manipulate our readings by calculations, not a live experiment. So we have to still put it across to everybody here that are watching this video. They have to listen very well and understand how the calculations are being done. Manipulations are not just done by just adding values at interval, at any interval that you want. That is nonsense. So when you want to manipulate values, there must be a formula. That is, physics has principles or laws. Every experiment comes from a topic, and there's a formula that will be used to obtain the values. So you don't just bring values and start writing them anyhow to fill up the table. That is wrong. So how do you know you're correct? After you've done your graph, the slope determines whether you're correct, because the slope or the intercept represents something. We have done the experiment on lens, on converging lens. That's number 1 for this alternative B is on our video. So if you watch our experiment, some of the intercepts and slope we are getting we got 15 cm, either intercept or slope. You can watch it. And that makes our manipulations correct, because the converging lens that is given to you has a focal length of 15 centimeter. So you don't have to solve, and at the end of the day, you'll be getting a value that does not in any way agree. Whether you do the live experiment or you got by calculations, your slope or your intercept must give a quantity that agrees with the values you are giving to, or with the focal length or whatever it is, moment inertia or whatever it is in the experiment. So you don't have to manipulate by just bringing fake values. You must work with formula. I repeat, you must work with formula. So in this experiment, WAEC did not specify any mass, but we are just using 30, 40, 50, 60, 70. So understand how the calculation is being done, because they may not bring 30, 40. What if they bring 20, 30, 40, 50, change the masses? So what will you do? So learn how to calculate it, learn how to repeat the calculations after watching the video, and then plot your graph and repeat the same graph, so that when the values or the masses are changed, you can still do the same thing and get your values and say plot and get your correct graph and correct slope. So let's start. For us to perform the experiment, we need a formula. This formula you are looking at, the formula have been derived using the principles of physics and further mathematics. So considering the rotation of the body, considering the moment of inertia, we're able to obtain a formula that relates the period. T is capital, that is period. And then the length of the meter rule, the capital L inside the numerator in the square root sign, that capital L is the length of the meter rule. Length of the meter rule, not length of the string. The length of the string is not used in the calculation because it's held constant throughout the experiment. So 2 pi square root of L, length of the string, 1 over 12 multiplying mr. mr is the mass of the meter rule. That R stands for rule, plus half m. That m is the mass, the different masses we are hanging at the center of the meter rule, 30 gram, 40 gram, 50 gram, as the case may be, all over mr plus m. The mr is also the mass of the meter rule, where the m is the mass we are hanging in each case or in each experiment, multiplied by g. That g is acceleration due to gravity. So this is the formula we need. So we raise t, capital T is the period of oscillation in seconds. Mind you, all the values on this formula must be kept in SI unit. So T is the period in seconds. MR is the mass of the meter rule. And then we're using a standard mass of 150 gram for experiment. So you can use this as well. So which is 0.15 kilogram divided by 1,000 to get it a kilogram. Then M is the mass of the object we're going to place at the center in each case, so which will vary. Then L is the length of the meter rule. The length of meter rule, every meter rule is 100 cm, but we're taking the SI unit, which is 1 meter. Then G is acceleration due to gravity, which is 10 meter per second squared. Then we take pi as 3.14, not 3.142. In most physics calculations are pi, normally we take it at 3.14. So going to the form, we make substitution to make the formula simpler. Replace pi with 3.14. We now have 2 times 3.14. Replace the length of the meter rule L with 1 meter. We have 1 outside the bracket, 1 over 12. Replace the mass of the meter rule with 0.15 kg in SI unit. That is 1 over 12 multiplying 0.15 plus half m. We don't know m yet. M are the mass we are going to load step by step all over. Then mass of the meter rule 0.15 plus m, the mass we're going to load, multiply by 10. G is the acceleration due to gravity. So we'll multiply at 2 times 3.14 give us 6.28. Bracket opens. So what 0.15 divided by 12 will give us 0.0125 plus half is 0.5 m all over, open the bracket, 0.15 times 10 under gives you 1.5, then 10 times n gives us 10 m. So we have the formula modified in this way. So everything is provided in this formula. So if by adventure you want to use a mass of 120 gram or a different mass, all you have to do is to replace 0.15 with the mass you want to use, maybe 0.1 to make sure that the mass is in kilogram. Divide that mass by 1,000. So if it's 120, use 0.12. If it's 130, use 0.13, and then modify your own formula. So our period is equal to 6.28 square root of 0.0125 plus 0.5 m all over 1.5 plus 10 m. So master this formula and then use it all through. All you have to do in each case, replace m with the mass you are asked to hang on the meter rule. So let's go to experiment number 1. So you see that table of value, we're already written the mass of the rule, meter rule, 150.0 grams, which we are selecting, we're using for the experiment. C, the center of gravity as 50.00 centimeter. You see your table, serial number, and the number of the experiment up to 5 times. Then the first, after serial number, you have mass in gram, time for 20 oscillation in seconds, period, T over 20, then period squared, which is second squared, then inverse of period squared, which is per second squared. So we'll start the experiment by using a mass of 30 grams. So number one, we'll write our mass as 30.00 to 4 SF, 30.00. So let's go to the calculation. The next thing is to find the period before any other, that is capital T, before any other thing. So for number one, when our mass is 30 grams, divide the 30 by 1000, we have 0.03 kg. Convert it to kilogram first, and then apply the formula above. So period equal to 6.28, then 0.0125 plus 0.5 multiplied by m, and our m here is 0.03, all over 1.5, which is in the formula, plus 10m, that is 10 times the same 0.03. So all you have to do is just replace m with 0.03 in this formula. You have that. So we evaluate. We now have 6.28. Evaluate the numerator. You're going to have 0.0275. Evaluate the denominator. That is 0.03 times 3 gives us 0.3 plus 1.5 gives us 1.8. So divide what you have inside the square root, 0.0275 by 1.8, and that will give us 0.0153. So we have 6.28 times 0.0153. So if you solve this, you're going to have the square root of 0.0153 times 6.28 will give us 0.777. We have to warn this. When you are looking for your period, keep your answer to 3 significant figures. 0.777. When you're getting your period, I repeat myself, capital T in all the calculations, keep your answer to 3 SF. Every other calculations you are doing here, keep it to 4 SF. So let's report our period 0.777. So our period for the 30 gram mass is 0.777 to 3 SF, but in report, when you report to the table, on your table, you put it to 4 SF. So that will have 0.7770. So let's go ahead to find our small t, which is the time for 20 oscillations. So our small t is obtained using number of oscillations times period. So number of oscillations is 20 according to the experiment. If you have to do 10 oscillations, then your n will become 10. So now I have 20 times the period, which is 20 times 0.777, giving us 15.54 seconds. 15.54 seconds. So this is your time for 20 oscillations. Small t, 15.54 seconds. So report our small t here as 15.54 seconds. So you can see that. Having done that, the next we'll do is find the square of period square. So you see the square of the period. Period is already 0.777. Square of 0.777 gives us 0.6037 to 4 SF. 0.6037. So the square of the period is 0.6037. Report it. 0.6037. That is the square of the period obtained. Then we'll now find the inverse of the square of the period. So t raised power minus 2, that the inverse of the square becomes 1 over t squared. That's what it means. That is 1 over t squared is 0.6037. So 1 over 0.6037, and that gives us 1.656. 1.656 per second squared. So here we have 1.656 reported. So summarizing, for the 30 gram mass, time for the small t, time for 20 oscillations is 15.54 seconds. Then period 0.777. Then period squared 0.6037. The inverse of period squared 1.656. All values recorded to 4 SF. The next experiment is we have to take mass, to hang a mass or to sellotape a mass of 40 grams at the center of gravity. So number 2, we have 40.00. We'll go to calculation. So after you have written your math, the next thing you do is to do the period, the capital T, before you do for small t. That is by calculation. For number 2, mass is 40 gram now. Convert the mass to kilogram, divide by 1000, that gives us 0.04 kg. Apply the same formula we derived, T equal to 6.28 root of 0.0125 plus 0.5 m all over 1.5 plus 10 m. Replace m now with the SI value 0.04 kg. So we now have T equal to 6.28 into square root of 0.0125 plus 0.5 multiplied by 0.04 all over 1.5 plus 10 times 0.04. So when we solve what we have in the square root, the numerator we're going to have 0.0325, the denominator we're going to have 1.9. Then divide the numerator by the denominator. You're going to have 0.0325 by 1.9, you have 0.0171. So solving out, square root of 0.0171 is 0.131. Multiply it by 6.28 that is in front of the square root sign. That will give us 0.8233 SF. As I said, find your period only to 3 SF. So when you report to 4 SF, but in calculation, keep it to 3 SF. So our period is 0.823 for the 40 gram mass. So let's report our work. So go to the period column and report capital T 0.8230 to 4 SF. So let's now find our small t. Our small t is number of oscillation times capital T. So you have to read the question very well and know whether you're asked to do it for 20 oscillation or 10 oscillation before you start using n as 20. So if n is 20, so we'll now say 20 times 0.823. 823 is a period, and that gives us 16.46 seconds as our time for oscillation, 16.46 seconds. We report our small t as 16.46 seconds. So as you can see there. So let's now go ahead and find period squared and the inverse of period squared. Our period squared, that is t squared, is 0.823 squared. 0.823 is the period calculated before. So 0.823 squared gives us 0.6773 to 4 SF, 0.6773. So report our work, 0.6773. So having done that, we'll now look for the inverse of period squared. The inverse of period squared, that is t raised power minus 2, is sent as 1 over t squared. And our t squared already is 0.6773. So 1 over 0.6773, that gives us 1.476. 1.476. So we report 1.476 at the inverse of periods of the square of the period. So summarizing, for the 40 gram mass, our time for 20 oscillation is 16.46. Our period 0.8230. Our t squared 0.6773. The inverse of t squared is 1.476. All values recorded to 4 second figures. We'll now go to the next mass, which is the 50 gram mass. That is 50.0, which is the third experiment, the 50 gram mass. So first of all, as we did for others, we'll find the period, capital T. So let's go straight to calculations. For the 50 gram mass now, we'll first convert, as I'll be doing, convert the mass to kg, divided by 1000, that gives you 0.05 kg. Then use the formula T equal to 6.28 square root of 0.0125 plus 0.5 m all over 1.5 plus 10 m. Replace m now with 0.05. So when you do that, you have T equal to 6.28 square root of 0.0125 plus 0.5, replacing m with 0.05 all over 1.5 plus 10 multiplying 0.05, where m is 0.05. So solving out, we'll have 6.28. So solving everything inside that square root, both up and down, we'll have 0.0375 over 2. And then that will give us 6.28 times square root of 0.01875. So if you divide 0.0375 by 2, you get 0.01875. So 6.28 multiplied by square root of 0.01875 will give us period of 0.860 to 3SF. 0.860 to 3SF. So now report period under period column as 0.8600. Keep your values to 4SF. 0.8600. So we'll now find our small t. So for small t, the formula remains number of oscillations times period. That is 20 times 0.86. That's the period. That gives us 17.20 seconds to 4SF. So small t is 17.20 seconds reported. So we'll now move over to find t squared and the inverse of t squared. T squared, that the period squared, becomes 0.860 all squared. That gives us 0.7396 seconds squared to 4SF. 0.7396. So now report T squared 0.7396 on that column. We'll now find the inverse of T squared. Inverse of T squared, which is 1 over T squared, which is going to be 1 over 0.7396, and that gives us 1.352 per second squared. 1.3. We'll now report here 1.352 are the inverse of T squared. So summarizing, for the 50 gram mass, our time of oscillation is 17.20, period 0.8600, T squared 0.7396, inverse of T squared 1.352, all values to 4SF. So we'll now go to the fourth experiment, where we are asked to take a mass, keep a mass of 60 grams at the center of gravity and set the meter rule into 20 vertical oscillation. So writing the 60 there into 4SF, we'll now calculate our period. That is, the next thing to do is calculate that period by the formula we derived. So for mass of 60 grams, convert to kg by divided by 1000, apply similar formula that will be using T, 6.28 square root of 0.0125 plus 0.5 m all over 1.5 plus 10 m. T equal to, substitute m now with 0.06. Make sure that you convert all your masses to kg. So that becomes 6.28 multiplying 0.0125 plus 0.5 into 0.06 all over 1.5 plus 10 into 0.06. Solving out, we have 6.28. The square root numerator gives you 0.0425. The denominator solved out gives us 2.1. So we now have 6.28 times 0.0425 divided by 2.1 gives us 0.0202. So when we solve that out, we'll have our period at 0.892. Period always kept in your calculation to 3SF. 0.892. So we'll now report it as 0.892. We'll now add 0 to make it to 4SF on the table. So you follow that. We'll now look for our small t. Our small t is n times period. N is number of oscillation, 20 times 0.892, and that will give you 17.84 second. 17.824 SF. So we'll have 17.84 second. 17.84 second. So we'll now go to period square, the square up. We'll have to square the period. So period squared is 0.892 squared. That gives us 0.97957. 0.7957. 0.7957 recorded on the sheet. We'll now look for the inverse of the period squared. The inverse of the period squared, that is t raised to power minus 2, is 1 over 0.7957. That gives us 1.257. So we have 1.257. So that is it. So summarizing for the 60-gram mass, the time of oscillation 17.84 seconds, the period for 20 oscillations 0.8920, the period squared 0.7957, then the inverse of the square of the period 1.257. We'll now go to the last mass, which is a mass of 70 grams, to be suspended at the center and set into 20 vertical oscillations. We'll now look for the period, capital T. Let's calculate it. For the 70-gram mass, as we're doing for other, the first we'll do is to convert the gram to kg by dividing by 1,000. That gives us 70 over 1,000, 0.07 kg. So we apply the formula period T equal to 6.28 square root of 0.0125 plus 0.5 m all over 1.5 plus 10 m. Replace m now with 0.07. So when we do that, we'll have period T equal to 6.28 square root of 0.0125 plus 0.5 multiplied by 0.07 all over 1.5 plus 10 into 0.07, replacing m with the mass in kg. That's the only difference you're making there. We now have period equal to 6.28. Solving at the numerator, we have 0.475. The denominator will have 2.2. So we now have 6.28 multiplied by, divide 0.475 by 2.2, you have 0.0216. So the square root of 0.0216 is 0.147 multiplied by 6.28. We have a period at 0.923. 0.923. So report our period as 0.923 to 4 SF. So having gotten our period, we'll do for our small t, time for the total oscillation. So small t is number of oscillation times period. That is 20 oscillations times 0.923. That is going to be 20 times 0.923. That gives us 18.46 seconds to 4 SF. 18.46. So report 18.46 on the table. So we'll now go over to find our period squared. The square of the period is 0.923 squared, and that will give us 0.98519 seconds squared. 0.8519 seconds squared. We report 0.8519 on the table. We'll now find the inverse of the square of the period. So we'll find 3 to the power minus 2, which is 1 over 0.8519. That gives us 1.174. 1.174. We report 1.174. So you can see that. So let's summarize our reading for number 5. For the 70-gram mass on the center of gravity of the meter rule oscillating, our time of oscillation, 20 oscillation, is 18.46. Our period is 0.9230. Our t squared 0.8519. Our t raised to power minus 2 is 1.174. So if you do your calculation, we use a calculator and do this is your t 15.4. Divide 15.4 by 20. You see you're going to get exactly 0.777. So do t squared, you're going to get 0.037. 2t inverse of t squared, you're going to get 1.656. That's the same way all through. So the important thing here is when you're calculating your period, this capital T, make sure that your value you're going to get must be kept to 3 SF. You can get a lot of values, but approximate them to 3 significant figures. I did not say 3 decimal places, 3 SF. Then after that, you can now calculate other values. Then when you're reporting your work on the table, report everything to 4 significant figures. 4 significant figures. 4 significant figures. I did not say 4 decimal places. You can see the consistency in our reading. And if you check out the reading, they are correct. The masses increase 30, 40, 50. The weight of the meter will also increase, and it will take more time for you to complete 20 oscillation. The time will also increase 15.54, 16.46, 17.20, 17.84, and 18.46. So in the experiment, the height, the length of the string doesn't matter. Even if they say use 70 cm as H, or use 80 cm as H, or 60 cm as H, it doesn't matter. It will not affect the reading. The distance between the two strings, which we kept at 80 cm, that the distance D does not also affect the experiment. So all these two are constant. Whether it's changed doesn't affect. So all you have to do is repeat the calculations using maybe different maths, using 20, 30, 40, 50. Or you can use 10, 20, 30, 40, 50, 60, and then repeat it and plot the graph. You get similar reading. So what are we going to plot? We're going to plot T inverse. We're going to plot, T square of T, square of inverse of T square, the last column, 1.656, 1.476, 1.352, 1.257, 1.174. We're going to plot these values on the vertical axis or on the ordinate against the mass. The mass is 30 gram, 40 gram, 50 gram, 60 gram, 70 gram on the horizontal axis or on the abscissor. So T raised to minus 2 on the vertical, and the mass is 30 raised to 70 on the horizontal axis. So let's look at the shape of the graph. So this is our graph. You can see we have a straight line but an inverse graph. This is a graph of T raised to minus 2. Unit is close to its second S raised to minus 2 on the vertical axis against m grams on the horizontal axis. And then for the scale, to cover the vertical axis, we chose a scale of 2 big buses, and 2 big buses means 4 cm, since each bus is 2 cm. 4 cm to 0.5 unit on the vertical axis. You can count 0.5, 1.0, 1.5, 2.0. So you see the vertical axis. So 4 cm to 0.5 unit. If you want to know what each line represents, divide 0.5 by, each line is 10 lines. Each bus is 10 lines. So 2 buses is 20 lines. So divide 0.5 by 20, and that will give you 0.025. So one line on the vertical axis is 0.025. Then going to the horizontal axis, we chose a scale of 20 cm to 2 cm. That is one bus, 2 cm to 20 units. So you can see 20, 40, 60, 80, 100, 120. We have to exceed the mass given to us on the paper. We have to exceed, move high, because we know that the graph is an inverse graph. So you're going to have an intercept on both the vertical axis and on the horizontal axis. You may be asked to read off the intercepts. So that's why the scale on the horizontal axis was reduced. So you can see it, so that the graph will have an intercept on both vertical axis and also on the both horizontal axis. So the scales were reduced, so it wasn't so lengthy. So having done that, we plotted the graph, and we have, out of the 5 points we obtained from our calculation, 4 points how to fall into the straight line, perfectly into the straight line, 4 points, and 1 was off, so we have to ignore that one. We took our slope from that point. On the higher coordinate on the vertical axis is 1.48, which is the point on the straight line. Then we took another point off the straight line, because the points on the straight line are very close to each other. So the lower coordinate on the vertical axis is 0.75. We'll now move down. So the higher coordinate on the horizontal axis is 1.06, while the lower coordinate on the horizontal axis is 40. So this is where we took our slope. So let's look at the slope. Question number is the slope S, which is the change in t minus 2 axis all over t raised to power minus 2 axis all over change in m axis, which is 1.48 minus 0.75 per second squared all over 1.06 minus 40 grams. So you can see that more clearly. So remember that the vertical axis, the unit is per second squared. Horizontal axis is mass, unit is grams. So having done that, so now the numerator gives us 0.73 per second squared, and the denominator gives us 6 grams. So we'll divide, the slope is 0.011 per gram per second squared. So that's the unit of the slope. So we're out to find in question S, Q equal to 0.68 over slope. We now have 0.68 all over the slope, which is 0.311 per gram per second squared. I will obtain 61.3 gram second squared. So you see, that is that. Then precautions for the experiment. The precautions, the likely precautions you should say is, I avoided error due to parallels in taking readings from the meter rule. I avoided error due to parallels in taking readings from the meter rule. Number 2, I made sure that the trays or the string used were tied firmly. I made sure that the strings were tied firmly. So those are the precautions you observe in this experiment. The other precaution is that you will say that I displaced the meter rule at a small angle to avoid vertical gyration. Gyration is spelled G-Y-R-A-T-I-O-N. So these are important precautions for this experiment. Then the next question we are asked here is, we are asked to define the center of gravity. The center of gravity of a body is the point at which the resultant weight acts, ACTS, at which the resultant weight acts, or the center of gravity of a body is defined as a point at which the resultant weight is concentrated. So you can go through the graph. You can use the value, use different values. You can use 20, 40, 60, 80. You can use 40, 80, 120, 160. Change the masses and repeat the calculations. And then you're going to still obtain similar shape or similar graph. You can still change your meter rule mass. Instead of 150 gram, you can use 120 gram or 0.1 kg. Mind you, in the formula introduced, all the mass you are going to input in the formula must be in SI unit. If your meter rule is 150 gram, you're going to use 0.15. If your meter rule is 120 gram, you're going to use 1.2. If your meter rule is 130 gram, you're going to use 1.3 in the formula. And everything will follow without any problem. So we have come to the end as we draw the curtain for this video. Number 3 question for alternative B, May, June 2024 physics practicals. So if you are not subscribed to this channel, come under the channel. The video is playing. You move down to the channel. Under the video, you see the subscription button or icon under the channel's name, Best Science Brain. Tap on that channel. Tap on the subscription button or icon only once and get subscribed to the channel. Get subscribed to the channel. Share our videos to your friends. Introduce your friends to this channel. This is Best Science Brand. Best Science Brand. Best, B-E-S-T. S-C-I-E-N-C-E. Brain, B-R-A-I-N. The words are joined together, no separation. So stream our videos and you see that we are doing good in this channel. We are teaching both for examination and also teaching ordinary classes. At the end of the examination, we still face ordinary tutorial on this YouTube channel. So get connected, invite your friends, share these videos, learn very well. Don't copy only readings. Know how to do it. Know how to do it. And also try to plot t squared. We did this plot was inverse of t against m. Go back to the graph and plot t squared, not the inverse, the period squared, capital T squared against m. Capital T squared, you can see them 0.6037, 0.6773, 0.7396, 0.7957, 0.8519. Capital T squared against M, 30, 40, 50, 60, 70. Plot this kind of graph. So instead of using the inverse, use T squared. This one going to give you a straight line that starts from 0, not an inverse graph, and find your slope. Because they can ask you to do anything from this graph, from this table of value. They can ask you to do anything. So see you next time in few hours from